Good morning, everyone. We'll begin in a few minutes. Yeah.
Look at the dog.
Hi, everybody. Good morning. Welcome back. All right. So, hi. Hello. So, we'll begin. I have a couple of announcements. Hold on a second. Let me get this straightened out here. So, great. Well, welcome back. Hi. I hope everyone had a fantastic spring break. I hope it was relaxing as possible with all that's going on. And I know it's so much for everyone. It's a lot. So I just want to acknowledge that. And there's a lot going on. And if you're, reading the developments every day, it's a lot to take in. So I appreciate that you're all here. Okay, we've got 37 participants, 38, so welcome everyone again. So I want to start with announcements that I have, which you probably read already, but I just want to go through them like I usually do. So we've got several. Let's share my screen. Did you see this comic? I laughed out loud. Can everyone see this? Are you seeing the whole thing? My whole screen? Okay, cool. All right. So let's go to our announcements. Okay, so yeah, you all are still here. I think that's awesome. You're doing great. I'm so glad to still be here, to still be able to do this with you. And so yeah, so do your best, keep at it. There's still plenty of time. If you feel like you had to withdraw for any reason, there's still plenty of time to make that decision. There is also an emergency withdrawal, which goes like beyond the semester, which is recognized by state financial aid, not necessarily federal though. So if you do decide to do an emergency withdrawal for which coronavirus would be eligible, just make sure you talk to your counselor. That's down here though, right? Emergency withdrawal, that's an available option for you. And then up here, I just wanted to show you this graphic, right? The growth mindset, 2 mindsets, a fixed mindset or a growth mindset. You can read through and see how reactions to challenges, obstacles, to efforts, to criticism and success of others can result in different ways of thinking, whether you have a fixed mindset where your intelligence is static, or a growth mindset where your intelligence can be developed. So just think about that as you go through, and like what happens when you're faced with challenges. Can you think about it in a different way to kind of use that to your advantage? And also the pass, no pass grading option has been extended. And so that's like college-wide, and you can use the e-form and self-service. That's where you registered for classes to do that if you want to. It might affect your transfer though, so talk to your counselor about that if you want to take that option. And you all got 5 extra points on exam 2 to make the average of 77, including your extra credit. So I took the average of the extra credit, the average of the exams, put those together, and then saw how many points I needed to give to everyone's exams to get the average up to a 77, and it was 5 points. Okay. You're welcome. I have a request for students to usually answer first. I was brought to my attention someone else wanted in a different class, and I'm sure it is also the same here, where they were requesting that people who are usually answering first and quick to grasp the concepts and putting in their answers into the chat box first, if you could hang back just for like 30 to 60 seconds to give other people a chance to think and to answer. And so yeah, so if you know that's you, if you're thinking that might be you, then yeah, if you could hang back, that would be wonderful. Thank you. And just an FYI, you might have already found out that the Canvas app doesn't work great for the quizzes. So if you can get a laptop or a desktop somehow, if you could borrow one, or maybe hopefully a lot of you took advantage of the loan program, that would have been great to get a laptop for that. Just for the exams, it's glitchy. It doesn't always work great, like especially with the uploads and stuff. And so just think about that. I know it's not possible for everyone, but do the best that you can. And okay, Monday's lab today. So we got this new virtual lab program that Sarah Gerhardt found, the lab instructor after my class, and I think it's pretty cool. The laptop program, they said early this week they would be sending out instructions with the protocol of how to get your laptop a lot earlier this week. And so you can sign up here with this course code for the new virtual lab platform. You don't have to do that like right now, or like you didn't have to do it yet. What's going to happen in my lab today, we're just going to be like question and answer, and I'll like show you how you can sign up for the lab platform. And then what you'll be doing to actually do the lab is following Sarah's instructions. Right here it says that you're going to watch her Zoom recording, which will be posted after her lab today, to carry out the lab as she instructs in the video. So today during my lab, it's just optional. You don't have to be there during my lab today, the scheduled time. I hope that my internet connection is unstable, but whatever. I think we're okay. Okay. So you don't have to be there with my lab today. I will be there though. I'll be answering questions, and I can lead you through how to log into the virtual lab platform if you want to. That's fine. But her recorded lab, Sarah's recorded lab, is where you'll be doing the lab from today, or whenever you can do it before it's due. And Sarah students, your attendance is mandatory during lab today. And then for Will students, I'm not sure what he would like you to do for your scheduled lab today, but Will students, you're welcome to come to my lab today. Okay, so Will students today, happy to have you. We can talk about what you'll need to be doing to prep, or any questions you have. I did email Will with some of your comments anonymously in the discussion board, just to let him know that you would appreciate his contact and letting you know, and his support. So yeah, you can come to my lab today. Okay, will students. Okay, is holding lab today. Okay, great. So you can come to mine still though, or you can go to his, or it looks like, is it mandatory, did you say, Adam? Okay, so you can come to my lab today, you can go to his lab today, but I would go to his lab either way. All right. So let's see. So then, yeah, the homework and lab reports, if you haven't read yet, they all have assignments now, like submission is for the assignment now, and so only PDF and JPG, so only image or PDF documents will be accepted. So if you have an iPhone, that HEIC file, I can't accept that because I'm not able to read it. I have to download each individual separate file and like put it on my computer and then look at it rather than looking at it through the computer through Canvas. So if you have an iPhone and you've been taking pictures and it's an HEIC format, then please just convert those into a PDF online. You can search like HEIC to PDF and do that for free. So that would be an option for you. Do your best to ensure that they're legible and right side up, but please don't email me if they're not. Just do your best, okay? And that's fine. All right, and the due dates are still on the Scalable Business schedule. What old link? There's no old link? Oh, you mean the one from the first lecture? Oh yeah, that's not even on Canvas anymore. I don't know where they got that, but tell them the new link is the only one in Canvas now. Yeah. Who should it, yeah. Okay, thank you. Sorry about that. I'm good. I mean, I'm glad that you noticed that. I should have mentioned that in the email, I'm sorry. Okay. So great. So there's a student resource list on Cabrillo. You can check that out for the COVID response. It doesn't have like money, but there is money available. There's emergency 500 grants available, $500 grants available. It should have been in an email from Sue Gotchis, or you can email Lauren Verduzco. Okay. And then also don't forget about the low cost and free Wi-Fi resources available for you. Okay. So check those out. There's extra credit, the Census 2020 chemistry poem. Don't forget about those. You can check them out in the assignments. Also, you have 5 points if you haven't done a connection session with me during open hours. So definitely do that. Tell me about yourself and we'll get to know each other. And that just brings me to reminding you to take advantage of open hours. And still, I'm not getting as many people as maybe would be best, because the more you take advantage of me, the more questions you can get answered and the more community you can make with other students too, because I'm hearing that a lot too, that like you're feeling like you're lacking your support system that you had before we went online, and I totally get that. And it makes sense then to make Zoom meetings with each other and form your study groups that way. That can totally be done. You can make your own now that you have a Zoom account. You can make your own meeting, invite people. You can make it open, and you can post that on the discussions. And yeah, that'd be a great idea. So also you have SI with with Francisco. He is on the same schedule. He has a Zoom link posted. I just posted his Zoom link in the modules. I think he also messaged you too. So same schedule, that's on the homepage of Canvas. Same schedule for me, that's on the homepage of Canvas. Do you want online tutoring? I can give you that referral. I just need to learn how to do it, but the email is in, so I'm going to figure that out. So email me with 30A OL tutoring in the subject line, and I will be able to do that for you. And apart from everything, right, I just want to, all that stuff, right, I just want to remind everyone about the central chemistry themes that really kind of tie everything together for us when it feels like things are disjointed and disconnected. Remembering that structure determines properties, right, and matter is particulate. meaning that matter comes in particles, little pieces, right? There's little pieces, those atoms, those molecules, those ions, those formula units, right? The compounds and stuff like that, and seeing how that kind of all ties together. So, Lauren, should I email the other students? All right. Okay, okay, so we're back on video. Yeah, I didn't notify anyone, I'm sorry. I just figured people were going back to the module to get the link like I have been, but you probably saved that link or you probably got it in an email, huh? Sorry about that. Yeah, I didn't think to remind people. Okay, let me, yeah, for sure. Let me just email everyone real quick. Okay. All right, cool. So good. So I emailed everyone, so hopefully they can come into this meeting. It looks like we got an uptick of 61. Oops. Okay. So this is where we left off last time. Right, and we had an energy diagram up on the screen, up on the board. Right, this is called an energy diagram, where no, there's no new link each time. It's just one link now. It's not. It shouldn't be too confusing. I'm sorry that it is. It's just the one link on modules. I'm so sorry. I assumed that everyone was going to modules to get the Zoom link every time, and I didn't think of the email. That was the original one. I'm sorry. Now it's just one Zoom link for every single meeting, just one. Okay, I'm so sorry. I didn't think of that. I'm sorry. So also I just wanted to address really quick too that like I read through all of your concerns that you have about the class. I appreciate your honesty there. And for the exam, like I said, I did curve it, so now the average is a 77, which is, you know, better than, a high C average. And I'm sorry that there were so many problems with the exam. Like I said, I didn't, I did the best I could. I hadn't thought of the things that you told me, so I really appreciate your feedback. I will change, and now I know how it worked and how it didn't work, and so I'm going to be thinking about that for the next exam for you and for my other class too. So I'm really sorry for all the stress it caused. I feel really bad about it. I didn't mean to, and I won't do that again. So thank you for hanging in there. So back to where we left off, which is about 2 weeks ago. So yeah, yep, exactly. So here's an energy diagram, right? We said that this is the system, right? The system for chemistry is the chemical reaction, right? The chemical reaction. So the reactants that go into the reaction and the products that come out, right? And so I have that up here, right? System, right? And so in blue is the system, which we have the reactants and the products, and this is the combustion of methane. So I showed you the combustion of propane in the balloon in the demo, remember, but the combustion of methane is just, you know, quicker and easier to work with, so that's what I have up on the board, right? Methane, oxygen. And so this energy diagram for this specific type of reaction shows that the reactants are at a higher potential energy, right? And this time I put potential energy here because that's what we're talking about when we're talking about the energy of the bonds in the reactants, and that's what we're talking about here, right? That the energy in the bonds of the reactants is higher, the potential energy, than the energy like contained in the bonds of the products over here. So we said that was a downward, right, slope from reactants to products. And so does that mean that this reaction had the, so what happens? So when the potential energy decreases, what had to happen? If the potential energy decreased in the system, how did that get offset? What happened to that potential energy? What happened to that potential energy that got decreased in the system? What do we think? What did we say happened? Right. What was the energy absorbed by? If this is the system and the potential energy went down, where was that energy absorbed? Okay, cool. So I'm getting a mix. Cool. Thank you for answering. What I'm seeing, so this is the system, which is the reactants and the products, okay? And so like the system itself has decreased in energy, right? And so then that means then that the people that were mentioning the heat going out to the surroundings were correct, because if the system decreased in energy overall, there couldn't have been heat going in that would have increased the energy, right, of the products, right? So heat had to be coming out. And so as we said, right, that the total energy of the system, or the total energy, is equal to potential plus kinetic. And so if potential goes down, right, kinetic had to go up and out of the system. Right? Kinetic energy goes out to surroundings. We'll say released to surroundings. Right? Kinetic energy released to the surroundings. So we'll see on the next one that the energy is absorbed into the system. This one is actually the opposite. This one shows that energy decreases, right, from reactants to products. And so the system actually decreased in energy, right? This is the whole system, the chemical reaction itself, right? That energy was released to the surroundings as kinetic energy. So the surroundings kinetic energy increased. So did this reaction feel hot or cold? Did the surroundings feel hot or cold? Yeah, hot, and it's exothermic, exactly. So then down here, the products of exothermic reactions have stronger bonds, like we said last time, right? We said that these products over here have stronger bonds, which makes them more stable right? So therefore, stronger bonds, therefore more stable, therefore lower potential energy. Remember that if you think of yourself like on the couch, relaxing, you're low energy, right? You're more stable, right? Same idea for the products. Yep, exo out, endo in. Exactly. So when the kinetic energy is released to the surroundings, right, we call that exothermic. Okay, other questions? Yeah, when the potential energy, that says, yeah, when the potential energy is being released, it turns into kinetic energy. So energy doesn't get created or destroyed during a chemical reaction, right? It just gets transferred. So when the potential energy releases, where does that energy go? It doesn't just disappear. It gets released as kinetic energy to the surroundings. It gets transferred into kinetic energy. And then this is RXN, thank you. RXN progress, RXN stands for reaction. Thank you for that question. Potential energy can only exist in a system. I don't know if I would say that. I would say that in chemical reaction systems, we are talking about potential energy, but I don't want to, it doesn't only exist in a system. But for our purposes, our system does involve potential energy because it's the energy stored in the bonds. Remember, we said one of the forms of potential energy is bond energy, right? Energy stored, that's potential. And so when we talk about potential energy in a chemical reaction, a system, then that potential energy that's stored is in the bonds. And so when that potential energy that's stored decreases, it has to leave, right, as kinetic energy because the energy has to be transferred, not just destroyed. I don't know if that helps. Products of exothermic reactions have stronger bonds, therefore they're more stable, therefore they're lower in potential energy. Sorry, just trying to get it to focus. Yeah, it's the same one, yeah. Electronegativity doesn't have anything to do with exothermic or endothermic. We're talking about a new topic. I think that that's not, I mean, I'd take that back. I mean, it does have to do with the polarity of the bonds as to how strong they are, but electronegativity doesn't directly relate to exothermic or endothermic. I know, I'm sure it's all cleared up. I'm sorry. Yeah, I'll go knock that one down too. So yeah, so this is just a review. This is what we had on the board last time when I was in the lecture room. So I just wanted to start here again to review. So yeah, all right. So let's do the next one. We'll do another energy diagram. Okay, so now we're going to talk about the other demonstration that we did with the frozen plank. So the frozen plank demonstration involved two solids, and they were both ionic solids. So they were barium hydroxide, octahydrate. So there were 8 molecules of water in the crystal structure for every formula unit of barium hydroxide. And that was mixed with solid ammonium chloride, 2 moles of ammonium chloride. And when those two things were mixed together, what happened was the chemical reaction allowed for the water to be liberated from the system. And that's why we saw it turn into that slurry where all of a sudden it was kind of getting more liquidy because the water was being like released from the crystal structure that it was in. And also there was a new combination of reactants to make water as another product as well. So actually 10 waters were a product, 10 moles or 10 molecules, either one. And there were 2 moles of ammonia gas. That's what I was smelling so strongly. It was like the strongest ammonia ever. And then another product is, so we have barium and chlorine, right? Barium chloride, that was another product of the reaction, which is then aqueous because there was water involved, and barium chloride is soluble salt. So please just think about the reaction later if you want to on your own time. It's not important so much as what got mixed together to form what as the energy that's involved. So we're going to talk about the energy. You can think about the actual chemical equation later and ask some questions about that later. So this is now our system. It's still a chemical reaction. So we're still going to draw an energy diagram to show the potential energy of the reactants versus the products. And so this is potential energy again. Right? And so say we have our potential energy of the reactants. Now is the potential energy, and this was, what did we say? This was endothermic or exothermic for the frozen plank? Yeah, good. The frozen plank was endothermic. It took heat from the water in order to have to get the reaction to occur. And so then does the potential energy, is the potential energy higher for the products or lower for the products? The products, though. Are the products lower or higher in energy, potential energy? Okay, cool, good. So I'm seeing most people answer higher, and it's true, right? Even if you didn't know that right off the bat, we're talking opposites here, right? We're talking about exothermic versus endothermic. We saw that exothermic, the potential energy decreased, right? Heat going out. This time, heat comes in, right? In the case of the demo, from the water, right? From the plank, from the air, from me when I touched it, right? Goes into the system, meaning that now at the end of the reaction, the system is higher in potential energy, or excuse me, the products, right, are higher in potential energy. So this system is higher in potential energy. And this time, the potential, or excuse me, the kinetic energy had to go in. So kinetic energy was absorbed by the system. I'm gonna try to get it to focus. It's hard without a lot of light. I'm sorry, y'all. I'm getting a new camera today. Okay, it just got worse. Hold on. Okay. So great. Great. So you said this was endothermic, or right? We said it was endothermic. So that means that the products of endothermic reactions have stronger or weaker bonds, do you think then? Right. Stronger is written up on the board, but that was for the last one, right? That was for exothermic. So it turns out then that the products of endothermic reactions have weaker bonds. That's what makes them less stable, which means they have higher potential energy. Yeah, so everything's opposite, exactly. So kinetic energy is absorbed by the system from the surroundings, right? Where did that energy go? Where do you think that energy went into? Why did this reaction, where two ionic solids were mixed together to form a gas, to form a liquid, to form an aqueous solution? Why, like, where did the energy go? Why is this an endothermic reaction? Why did energy needed to be absorbed from the surroundings? Why do you think? Any ideas? Like, where did that energy get used? What did it get used to do? It did get, you know, it is stored in the product's bonds now, that's for sure. But in the beginning, so energy doesn't get absorbed to make ice, energy gets taken away to make ice, right? So the energy was taken away from the water. So where did that energy go into? Exactly, exactly. Sophie, nice one. It was the crystal lattice to break apart those ions. Exactly, right? Those ions are super strongly like held together right in that crystal lattice. So to get those ions to break apart to make a new combination in the products required energy. That's exactly where it went to. Yep, split up the ammonium chloride, split up the barium hydroxide with the water molecules in the crystal structure. Exactly, okay. So had to go somewhere and it went into breaking apart the ions. Yep, okay. Questions here? Exothermic, endothermic, anything here? Yeah, exactly, to make the new combination. Other questions? We have 67 here. That's really good. That's pretty much how much we have in any lecture. So I'm happy about that. Other questions, anyone? Okay, so rather than producing heat, it broke up ions which created cold. The heat came from the water to break apart the ions, exactly. The heat came from the water, right? So that heat that was taken from the water was used, that energy was used, that potential energy, that kinetic energy came in and started shaking apart those ions, right? And when it did, that energy was absorbed, right, into the system. And so now those products have that potential energy stored. So that transfer from kinetic into potential. I don't want to get too close. I don't want it to focus, but let me go up. What was the next? Okay. Does that make sense? It didn't, it was more like, I would say it's not like creating cold, it's just that heat was taken away, kinetic energy, therefore heat, right? Heat is the transfer, the flow of kinetic energy. So the flow of kinetic energy from the water to the system meant that now the water didn't have that kinetic energy anymore, so it froze. You can't tell whether the product is higher or lower in energy just from looking at the equation. You would have to be given a number, which we're going to go over in a minute. Good. Misha, what did you mean by the ions of the product? Oh, the reactants, right? These are the ionic solids, right? The reactants were solid ionic compounds, right? Meaning that they had a crystal lattice, those ions were strongly attracted to one another, right? And so to break those ionic attractions apart, it required energy to do so, and that's why it took kinetic energy from the water to break those ionic attractions. Good? Okay, good. All right, so let's move on to okay, so let's think about some, oh, what's your question, Lauren? Yeah. I'm gonna write up on the board while you ask me. I wish we could do a real think, pair, share. So in the reactants, the water was part, did you see that dot in between the barium hydroxide and the water? That dot meant that it was associated with the barium hydroxide. So for every barium hydroxide formula unit, there was one molecule of water within the crystal structure too. So the barium hydroxide, sometimes ionic solids have water like in the crystal structure too. So overall, the barium hydroxide octahydrate, it's called, was a solid. In the reactants, it was a liquid because it got released from the crystal structure as the reaction proceeded. Okay, so let's think about these processes, like, really, in everyday life. Okay, and assign whether they are endothermic or exothermic. So yeah. I wish it could be a real think, pair, share, but you all can comment with each other. Activating a hand warmer. Or what about ice melting? these are all the systems, okay? So like the system is the ice, the system is the hand warmer, you know, the stuff inside. What about the system of sweat evaporating? What about cooking food, where the food is the system? What about metabolism? Which is the overall reactions in the body, all of the reactions in the body combined. And we'll call it reactions in a human body. What about running a car? And like, feel free to like chat with each other. At other times I'll do like, I'll see if I can do like a breakout Zoom. I think you can do like a breakout chat with people. It'd be cool if it was randomly assigned. I don't know how that works, so I'll figure that out, but you can chat. Think about the heat. All you have to think about is the heat involved. Does it get cold and like absorb heat, or does it get hot? Like, can you feel, do the surroundings get hot so the system releases heat, or do the surroundings get cold where the system absorbs heat? So what do we think about for A? What do we think for A? And we'll start there. Cool. Yeah. How do you know it's exo? How do you know it's exo? Right? Heat is being released to your hands, which is the surroundings. Yeah, exactly. So good. Exo. What about ice melting? Do you all want to talk about that? Okay, so what makes you say endothermic for ice melting? Yep. Right. Right. Yep. Yep. Yeah, that's right. Exactly. And you can think of it too as the opposite of freezing, right? We just saw that freezing the ice like took energy away from the ice, right? But melting the ice means that energy has to go into the ice. So good. Energy into the ice to melt the crystal structure of the ice, right? Takes energy, so endothermic, yes. Good. And so what about sweat evaporating? Cool. Yeah, so Liliana, Elva, Savannah, someone else I'm forgetting, but you all said endothermic. Yeah, JJ, exactly. So it is endothermic because what does it feel like when sweat evaporates, right? Does it feel like it's cooling you or warming you up? Right. The whole point of evaporation, the whole point of sweating is to cool you down, right? So that means that when sweat evaporates, it is an endothermic process because it's taking heat from your skin, right? Taking heat from your body, right? To cool you down. So to go from a liquid state, right, sweat, to a gaseous state takes energy because it's going from a more ordered liquid state to a less ordered gaseous state. Just like it takes energy to melt ice going from a more ordered solid state to a less ordered liquid state. So it's kind of like the next step, right? Melting and then evaporating. So they're all endothermic, cooling you down. Yep, the gas is less ordered, we'll say. Yep. Exactly. So it's cooling you. The people that said exothermic, does that make sense now after the explanation? Or can I help clear that up again or more? Okay, cool. Okay. So what about cooking food? What about the food? Is the food an endothermic? Is it endothermic for the food or exothermic for the food? Yeah, the food is the system. The food is the system. Yeah. Good. Yep. The food is the system, so it's absorbing heat from whatever you're cooking it with, exactly. So endothermic. So, yeah, so that's another, like, we have to think, like, what's the system, what's the surroundings? So when you think cooking, you think immediately heat, right? But for the heating element, that's exothermic, right? The heating, the stove is producing heat, so the stove is exothermic, right? But the food, for the food, it's absorbing heat, so it's endothermic, right? Absorbing the heat. So what about metabolism? Overall, in the human body, is energy being released or absorbed? Right, released or absorbed. So does that mean it's endothermic or exothermic? Exactly. Yeah, we're releasing heat. We absorb energy in the food that we eat, but overall, it's exothermic. Overall, the reactions in the human body are exothermic, right? Which is how we live, right? That's how we are able to do the processes, how the body is able to perform the chemical reactions that are required to sustain life, right? And so yeah, exothermic. I'm not sure, so the last two questions, do you mind rewording those, please? Right, yep, so the metabolism itself, the reactions in the human body. So the reactions in the human body are the system here. Like the overall, I'm talking about overall. Just overall, yeah. Overall, energy is produced, right, in the human body. If it wasn't, then there wouldn't be enough to carry out the chemical reactions required for sustaining life. Okay. Okay, other questions there? Did that help? Okay, so what about running a car, where the car is a system, like the engine, the combustion? Awesome. Yeah, so it is exothermic for running a car. Yeah, and you can tell because the car warms up over time. You can tell because energy had to be produced in order to run the car. Kind of like for the body, right? This is kind of like a similar idea, right? Like, yeah, there's a bunch of different processes like happening in the car and energy is being used in the car, but the energy had to come from somewhere, right? It comes from the combustion reactions in the car, just like the energy in the human body comes from combustion reactions in glycolysis and the citric acid cycle and the electron transport chain. So in fact, metabolism is the same as combustion, which I think is fascinating. Right, you can think, I've never thought of this before, but these are like two of a very similar concept. Like if you can conceive of the car being exothermic, because it's running the car and it gets warm, right? You can think of the body as exothermic because it's running the body and also producing heat, right? And it's like I just said, like metabolism and combustion are the same thing. They have the same overall reactants and products. The fuel goes in, it's got carbon and hydrogen, oxygen is required, right? Carbon dioxide comes out in the breath we exhale, water is produced at the last step of the citric acid cycle, and energy is also produced. So they're both exothermic, metabolism and combustion. Yeah, overall though, when we think of overall, right, overall there's energy produced. Okay. Okay. I think there are like little emoji options, aren't there? Like, I think I enabled that where you can do a little, yeah, there you go, thumbs up. Sweet. Okay. All right. So let's move on. So we've got some energy units you want to talk about real quick. I'm just going to talk about the energy unit that we're going to be using in Chem 30A. Okay, and so you can think about this, everyone. Think about what's happening when you're cooking food. Think about what's happening when you like break an ice pack, right? Or when you're freezing ice, or when you're boiling water, right? What's happening on that particulate level? Like, are the particles for freezing, right? They're becoming more ordered, so they're releasing energy. Whereas if the ice is melting, they're becoming less ordered, so it requires energy to break the ice, you know, apart. And you can think about that, and you can ask me questions as they come up to think about endo or exothermic. Remember too that there are videos online in the modules. So we're in week 9 right now. So this lecture is posted in the modules. The image I'm about to show in a minute, if I get to it, is posted in the modules. The extra videos and resources are posted in the modules. So make sure that you're always going back there too to get extra insight and extra practice. Okay, the homework's posted there and everything. I would tell you if I needed to. You would always know that the chemical reaction is the system. I would need you to know that, but I will be specific otherwise, yeah, about telling what's the system and the problems. Yep. Yeah, and you're right. I will. I usually do say system. Yeah. even when it is the chemical reaction, which you should know, but I do say system when I say even chemical reaction. Yeah. All right, so energy units. So this is 6.1 A and B. So I think Franny, you asked the question, what was the section earlier? This was all just in section 6.1, and then also I kind of just took it among my took it upon myself to kind of just give this overview from the last 2 lectures. It was kind of just like me making it all come together because the chapter doesn't do the best job of like laying it out like that. But now in section 6.1 AB, just real quick energy units. We're going to use calories and kilocalories, where 1 calorie is the amount of heat needed to raise 1 gram of pure water by 1 degree Celsius. That's the definition of a calorie. It's a unit of energy. Good, I'm glad, Franny, thank you. Yeah, so a unit of energy, and this is related to the calories that we see on a food label. And so I'm going to talk about that for a minute today. So on a food label, 1 calorie, so that's with an uppercase C. So 1 calorie with an uppercase C is actually equal to 1,000 of these calories. And so when we see like something has 300 calories on a food label, that uppercase C, that means that it would have 300 times 1,000 of these lowercase calories, meaning the heat needed to raise the 1 gram of water by 1 degree Celsius. H2O over here, water. And 1,000 calories, how many kilocalories is that? 1 kcal. So this is the energy unit that we're going to use in Chem 30A, right? And so this means then that 1 kcal, that's the same as a food calorie. So it'll be interesting, therefore, to use kilocalories in this class, because then we can always be relating it back to food. We can always think about how much that is in relation to a food label. Okay. So let's do that. Let's figure out how many calories are in a tablespoon of oil, right? Any oil, if you look on the food label, contains about 14 grams of fat. Focus. It's not going to focus, sorry. But this food label does say 14 grams of fat for that oil per tablespoon. So let's talk about metabolism really quick. Actually, let's talk about food. Okay, so on a food label, so energy is stored in the chemical bonds in the food. Okay, so that means then when we talk about like the calories in, say, the tablespoon of oil, right? That means then that the energy, the calories that we're talking about are the energy stored in the chemical bonds of that food, of that oil, of whatever it is, right? And so then we can figure out, so what happens in the body, right? Metabolism breaks down these food molecules and uses that stored energy, like we talked about, to produce, right? It turns it into kinetic energy, which is used to carry out chemical reactions in the body. It's used to, therefore, let our bodies move and breathe and think, and our hearts to beat, our, digestion to occur. All of those processes require energy, and those come from that energy comes from the stored energy in the chemical bonds in the food. So let's figure out, so then we can talk about food energy, right? Where proteins have 4 calories per gram. Carbohydrates have also 4 calories of stored energy per gram. And fats have 9 grams of stored energy calories per gram. So if we're talking about the amount of calories in 1 tablespoon of oil, so let's ask the question, how many calories? In 1 tablespoon of oil. How many calories? Sorry, it's getting blurry down there. I'm sorry. So how many calories are in 1 tablespoon, which is 14 grams of oil? how many calories in 14 grams of oil? So first, let's think, thank you. Hold on now. Let's think, is oil fat, carb, or protein? Good. Yep, oil is fat. Exactly. Are all fats bad for you? Brains actually love glucose. The brain energy is strictly glucose, actually. But you're right, not all fats are bad. Actually, so many fats are so good. Olive oil is a great fat, right? But brain energy is strictly glucose unless you go on a keto diet and then it switches over to the ketones. But yeah, brain energy is strictly glucose. So like the fact that all life on earth metabolizes glucose for energy, like that right there tells you how important it is, right? And the only energy that is used in the brain is glucose. But good, not all fats are bad. So how do we do this? Let's see, we've got our original unit, right? Our desired unit is calories. Our original unit is grams, right, of oil. And so we can write that first. And use the conversion factor right here. We're going to use this conversion factor, where that means we're trying to get calories. So 9 calories goes on top, and for every 1 gram of fat, right, which is oil. And so 14 times 9, and these are measured numbers. So 126 gets rounded to I think I take that back, everyone. Yeah, I think I take that back. I think we're gonna call these definition. So thank you. For you that said 130, it was true. If I had said that this was a measured number and rounding it to just 1 sig fig, wouldn't have been correct. This, we're going to use the 2 sig figs from the 14. Yeah. Were there questions up there? I'm sorry, I missed them. Yeah, glucose is a carbohydrate. Yep. It's the simplest carbohydrate that we use for energy. Take Chem 30B and you'll learn about all of that. I wish I was teaching it again, but yeah, Chem 30B was my forte for a while. So I love food chemistry. Well, you know, food macromolecule chemistry. Okay. Other questions here. And if you look at the label, by the way, so this does actually say 126 calories. But when we're thinking about significant figures, we're going to round it to 130. So yeah, on the label here of this oil, right, the serving size is 1 tablespoon. And that means then that there are 126 calories in 1 tablespoon because that is 14 grams. It also tells you here, it should, oh no, it doesn't tell you the number of grams, but oh no, it does. Yeah, total fat, 14 grams and 126 calories. Yeah, it's uppercase C. And it does matter because remember that 1 calorie, right? The food calorie is equal to 1,000 lowercase calories, which is the heat needed to raise 1 gram of water, which is 1 kcal. So you could say cal or kcal. Okay. Yep, exactly, Ireland. Yep, up here. Right? 1 calorie is equal to 1 kcal. Uppercase C. Okay, so I need to I bet it's unfocused. I'm gonna try again. Let me just I need to continue, so we'll get it focused again. But I need to continue real quick. I just need to, like, in the next few minutes, just describe where we're going next so that you know what it means for your lab. Yeah, and I'm getting a better camera today. I'm literally picking it up at 2:15. So next time it's gonna be much better. So we've been talking about all this heat, right? We've been talking about the surroundings that are cold or hot. So recall that heat, right, is the transfer of what kind of energy? Heat is the transfer of what type of energy? Ooh, that. Sorry. Heat is the transfer of good. Thanks for completing the sentence. It is kinetic energy from high to low. So heat is the transfer of kinetic energy from high to low. Excuse me. We can also call this thermal energy. We can call it thermal, We can call it thermal energy when we were talking about atoms and molecules. Kinetic energy is like macroscopic, right? And we've been using it, we can talk about it, but like when we're specifically talking about atoms and molecules, we call it thermal energy. Right, we can talk about kinetic energy like more on a larger scale, and we can still use it to talk about atoms and molecules, but there is a specific name for that type of energy when we do talk about atoms and molecules. And so that has a name, it's thermal energy, and this thermal energy even has a more specific name, and we call it enthalpy. So also known as enthalpy in section 6.2. Okay. So thermal energy is a specific form of kinetic energy, and that thermal energy specifically has a name, enthalpy. This comes from Greek, meaning heat within. So thal for thermal, right? N within, so enthalpy is the heat within the system. Okay, so we can quantify meaning we can give numbers to it. Using delta H, which means the change in, you can think of H for heat. I had one student the whole semester, like for weeks after learning about delta H last time, she thought that H was hydrogen. So H is not hydrogen. Yes, they're both uppercase H, but you can think of this H this time standing for heat. So we use a term, right, called delta H, which tells us the change in the heat of the system. Okay, so when we're going to do another type of energy diagram, but this time using H to specifically talk about the heat in a chemical reaction, right? The enthalpy. We use a symbol of uppercase H for enthalpy here. And we want to talk about the change in the enthalpy. Does the enthalpy go down? So was this endothermic or exothermic again? Good. The triangle means change in, yeah. And that's a delta. That's a delta, uppercase delta. So we say delta H. Good. This was exothermic. And just give me one more minute to explain this. This was exothermic, right? Good. So did H go down or up? Is delta H negative or positive? Very good, everyone. So check it out. This is one time where it's not opposite, right? We've had all these opposites with gaining and negative and positive and all that. This is one time where if energy is going down, delta H is negative. So going down is negative. So here, right? Yeah. The sign for delta H is negative because it is decreasing from high to low. So a negative delta H tells us that heat is what? Released or absorbed? Right. This means that when delta H is negative, so we're going to see numbers here next time, we just haven't talked about the numbers yet, that heat is released to the surroundings. Okay. So we don't see numbers yet. We're going to see numbers next time. And when you see a negative number for delta H, you'll see like delta H equals something. And when that number is negative, that means it's an exothermic reaction, right? This delta H is the change in enthalpy. So meaning the change of the heat within the system. And when it's negative, that means it went down. And we already know that when an energy diagram goes down from reactants to products, by the way, this is reactants, right? This is products, then it's exothermic, and so that's now how these are connected. So when someone asked before, how do you know when just looking at the chemical equation whether heat is absorbed or released? The only way you can know is if I give you the delta H, and I will be doing that. Okay, so that concludes our lecture for today. Don't forget about open hours. Remember, I reminded you earlier today too, so make sure that you come to open hours. You will be getting into more of this next time, of course. This just gives you an overview for your lab today. Enthalpy is just like another word for the thermal energy of atoms and molecules, which is also, yeah, anyway, so good. So it's another word for the thermal energy of atoms and molecules. And when we talk about the system, we can talk about whether that energy is going up or down for a negative or a positive delta H. So that concludes our lecture today. I just want to like let that go. Yeah, the open hours are the same as it always is. And ask your questions to me. You can ask questions in next lab too. So remember, Will's lab, you're welcome to come to my lab if you want your questions answered, but you also did get a message from him that tells you that you will be having lab today. So yeah. I'm not going to be using ConferZoom. All I'm doing is posting the links in the modules. Yeah, Sarah Lab. Yeah. Go to Sarah's lab. It's all in the announcement. Look in the announcement. Yep. You're welcome. Thank you all. Thank you so much. So see you in my lab and open hours today, okay? Thank you.